Early artificial intelligence collapsed into a prolonged winter when primitive single-layer perceptrons failed to resolve non-linear data structures. The mathematical bottleneck completely paralyzed industrial pattern recognition systems worldwide. Simple binary decisions functioned adequately, but complex real-world enterprise applications required non-linear separation boundaries. The structural inability to compute basic XOR logic gates halted commercial, multi-layered application development. Corporate enterprises discovered that single-layer systems could not scale beyond elementary, highly idealized data distributions. This architectural limitation triggered widespread disillusionment, causing massive capital withdrawals across global technological markets. Engineers lacked a mathematically sound methodology to adjust internal weight layers hidden from direct output observations. Without systematic credit assignment mechanisms, training deep network topologies remained an intractable computational impossibility. The connectionist movement emerged to challenge traditional symbolic artificial intelligence paradigms by introducing distributed representation frameworks. This paradigm shift focused intensely on mimicking biological neural pathways to process highly unstructured informational streams. By proposing networks of simple interconnected processing elements, researchers aimed to achieve emergent computational intelligence. This collective computational approach promised unprecedented resilience against noisy, incomplete, or corrupted enterprise data fields. The definitive breakthrough arrived with the formal, mathematically rigorous codification of the generalized backpropagation algorithm. This foundational mechanism enabled multi-layer network architectures to map arbitrary, non-linear functional relationships efficiently. Empirical data validated by institutions like Mila Research on algorithmic scaling laws confirmed that multi-layer networks successfully bypassed early computational convergence limits. Neural architectures finally demonstrated reliable multivariable pattern discovery. By linking continuous error propagation steps directly to internal parameter adjustments, deep computing paradigms became viable. The enterprise landscape shifted permanently from rigid expert systems toward dynamic, self-correcting statistical learning models. This masterclass dissects the underlying calculus of early error propagation frameworks powering modern deep architectures. We examine the exact mathematical orchestration required to navigate multidimensional loss landscapes with absolute precision. To understand the solution, engineers must first analyze the precise mechanics of multi-layer feed-forward neural networks. Data flows sequentially from input fields through multiple hidden arrays before reaching final prediction vectors. Every individual connection within this dense matrix possesses an adjustable weight representing signal transmission intensity. Synthetic biases shift activation thresholds, allowing individual neurons to activate selectively based on inbound numeric configurations. Hidden layers act as internal feature extractors, transforming raw input elements into increasingly abstract representations. This progressive abstraction allows the system to identify complex hierarchical relationships hidden deep within datasets. Without nonlinear activation functions, stacking multiple hidden layers collapses mathematically into a single linear transformation. Activation mechanics like sigmoids inject necessary nonlinear properties into the overall network architecture. The forward pass concludes by computing a scalar value representing total network variance from targets. This objective evaluation metric is formally defined as the enterprise system's specialized loss function. Quantifying prediction inaccuracy requires selecting an appropriate loss formulation tailored to specific downstream industrial tasks. Mean-squared error functions dominate regression operations, while cross-entropy metrics govern complex classification pipelines. The loss function maps the entire parametric state of the neural model onto a single, multidimensional geometric surface. This complex, multivariable topological map is universally known as the model's loss landscape. The ultimate objective of network training is to locate the absolute lowest point within this terrain. This optimal state corresponds to a parameter configuration minimizing operational errors across production environments. Analytical methods cannot directly compute this optimal state due to the extreme dimensionality of corporate datasets. Systems must rely on iterative optimization strategies to navigate the vast parametric space systematically. Gradient descent provides the fundamental mathematical locomotion required to explore these complex, high-dimensional error topographies. It directs parameter adjustments along the line of steepest local cost reduction across the map. The backpropagation algorithm operationalizes gradient descent within multi-layered networks by leveraging the calculus chain rule. This foundational mathematical rule decomposes complex global derivatives into manageable sequences of local partial derivatives. Calculus dictates that the partial derivative isolates how changing a single specific weight alters total error output. This localized sensitivity analysis forms the baseline metric for all automated parameter optimization. The error propagation sequence initiates at the final output layer by comparing predictions against ground truth. The resulting initial gradient reflects the immediate error rate relative to final layer activities. Using the chain rule, this output gradient multiplies against the derivative of the final activation function. This mathematical operations identifies exactly how layer inputs influence the terminal error scalar value. Using the chain rule, this output gradient multiplies against the derivative of the final activation function. This mathematical operations identifies exactly how layer inputs influence the terminal error scalar value. For any given hidden unit, the incoming error gradient equals the weighted sum of terminal errors. This elegant formulation allows internal parameters to calculate adjustments without direct output layer access. Partial derivative calculus loops continuously evaluate how internal biases affect the overall system error metric. Biases adapt alongside weights, providing complete mathematical flexibility across every structural tier of the model. Research from the IISc Bangalore Artificial Intelligence Lab demonstrates how tracking optimization gradient stability prevents extreme parameter variations. Maintaining stable partial derivative trajectories ensures consistent convergence during intensive training cycles. Every backward pass generates a precise collection of parameter gradients across the entire model architecture. These mathematical vectors indicate the exact direction and magnitude of necessary structural weight modifications. By automating these complex calculus loops, backpropagation eliminated the need for manual rule adjustments. Networks independent of human intervention began self-correcting internal parameters based strictly on empirical performance data. Despite its theoretical elegance, deploying early backpropagation within production environments exposed significant algorithmic vulnerabilities. High-dimensional loss landscapes frequently present treacherous topographical anomalies that stall standard gradient descent optimization routines. Local minima represent suboptimal valleys where local gradients drop to zero, halting further parameter modifications entirely. Early networks often became trapped within these deceptive zones, failing to reach global optimization targets. Saddle points present an even more pervasive architectural challenge within high-dimensional corporate data optimization spaces. These structures exhibit slopes that descend in certain directions while simultaneously ascending in alternative geometric lines. Standard optimization routines lose momentum near saddle points because the local error gradient approaches zero. Systems stall indefinitely within these flat regions, severely degrading overall training efficiency and model performance. Exploding gradients present another severe systemic hazard when training deep multi-layered network configurations over time. Repeated multiplications of large derivative values across numerous layers cause exponential parameter growth during optimization. This numerical instability causes massive weight oscillations, completely destroying learned patterns within the matrix. Systems experiencing gradient explosions fail to converge, leading directly to catastrophic model failure during deployment phases. Conversely, Vanishing gradients occur when small derivative values pass backward through deep network topologies. Successive fractional multiplications cause the error signal to diminish exponentially before reaching initial hidden layers. Without sufficient gradient signals, early foundational layers cannot update their respective internal weight allocations effectively. The network ceases learning complex, low-level features, limiting its overall multivariable pattern recognition capabilities. Engineers mitigate these mathematical hazards by implementing advanced weight initialization techniques and adaptive step controls. Bounding initial weight ranges prevents early parameter saturation, protecting backward derivative propagation channels from decay. Strategic parameter tuning transforms optimization pathways from fragile mathematical exercises into robust enterprise processes. Overcoming these fundamental calculus limitations laid the bedrock infrastructure for scaling modern deep learning models. Transitioning backpropagation models from theoretical frameworks into production enterprise environments demands rigorous execution protocols. Engineers must formalize step-by-step life cycles to guarantee deterministic results across highly distributed computing infrastructure arrays. The operational pipeline begins with meticulous data preprocessing and normalization across all inbound informational channels. Scale alignment ensures input features contribute equally to initial forward calculations, preventing artificial gradient imbalances. Next, deployment teams initialize the neural network utilizing tiny, randomized weight configurations bounded by mathematical limits. Proper initialization balances internal signal variance, ensuring active derivative propagation during early training iterations. Production pipelines execute forward calculations across unified data batches to optimize matrix multiplication throughput. Distributed hardware accelerators process these numerical operations concurrently, maximizing computational efficiency across enterprise cluster architectures. The automated system records intermediate activation states for every hidden layer during forward passes. Retaining these numeric values is structurally essential for computing localized partial derivatives during backward passes. Once forward computations terminate, the loss layer generates the primary error scalar value automatically. This metric serves as the foundational trigger, initiating the highly synchronized backward calculus propagation pass. The optimization engine transmits partial derivatives backward through compiled execution graphs using optimized driver code. Hardware registers dynamically update internal weights by applying calculated gradient deltas multiplied by learning rates. This iterative optimization cycle repeats across thousands of computational epochs until error metrics stabilize. Convergence validation protocols monitor performance shifts continuously, preventing models from overfitting specific training distribution samples. The deployment lifecycle concludes by freezing optimized parameter weights and exporting compiled network graphs natively. These static files execute low-latency inferencing operations across variable enterprise hardware topologies without modifications. Backpropagation remains the absolute baseline metric for modern neural tuning across all industrial use cases. Understanding this foundational calculus allows enterprise architects to build highly scalable, automated intelligence systems. The automation of weight updates via backpropagation caused a monumental macroeconomic shift across software development industries. Eliminating manual code rule adjustments drastically reduced long-term total cost of ownership for enterprises. Traditional software engineering models relied on humans explicitly programming every logical branch and edge condition. This manual approach proved completely unscalable when confronting hyper-complex, unstructured corporate big data environments. By enabling networks to self-correct weights autonomously, backpropagation fundamentally inverted traditional system creation paradigms. The data itself dictates the optimal functional mapping, accelerating enterprise deployment timelines across diverse industrial sectors. This technological pivot triggered a profound transformation within the global technical engineering labor market. rigid programmatic rule definitions gave way to advanced statistical model optimization and data pipeline architecture. Global employment metrics tracked by the International Labor Organization Future of Work Index document rapid shifts in labor share dynamics. Demand for traditional software maintainers declined while optimization specialized roles expanded. Organizations must proactively upskill engineering workforces to master multivariable calculus concepts and statistical validation models. Human expertise shifts from direct line-by-line coding into high-level algorithmic architecture oversight and training design. This labor reallocation maximizes corporate operational efficiency by automating routine data processing tasks completely. Human intelligence focus redirects toward defining strategic reward objectives, loss constraints, and enterprise alignment guardrails. The connectionist movement proved that mathematical optimization combined with scalable architectures beats manual rule engineering. This enduring architectural principle serves as the baseline bedrock supporting current frontier generative intelligence models. As enterprise tech architects navigate modern agentic deployments, understanding early gradient calculus remains absolutely mandatory. Mastery of backpropagation ensures your organization builds secure, deterministic, and highly efficient cognitive infrastructure. Stop guessing your tech strategy and wasting your time. Subscribe to Enterprise Tech Brief right now. We deliver zero-hype, pure architecture, the blueprint of enterprise intelligence. Completely free. Hit the subscribe button